All right, we're going to solve one more 3 by 3 system of equations, and we're going to see something else unique happen here. We're still going to use Gaussian elimination, which means we still need to get rid of these three terms. I'm going to rewrite the first equation because we don't want to change anything in that. And then what we'll do is focus on getting rid of the two x's in the second and the third equation. So what we're going to do first is get rid of this 2x. The way that we can do this is we can take 2 times the first equation and then subtract the second equation from that. If we do that, 2 times x is 2x, and 2x minus 2x is nothing, so that goes away. Here, if we take 2 times this one, 2 times negative y is negative 2y, and then if we subtract y from that, that gives us negative 3y. Then we're going to do the same thing here. 2 times 5z is 10z, and 10z minus 4z is 6z. And lastly, 2 times negative 2 is negative 4, and negative 4 minus 2 is negative 6. Again, we got this by taking 2 times equation 1 minus equation 2. And to get rid of the 2x in the third equation, we can take 2 times equation 1 minus equation 3. So we're still taking equation 1 and multiplying it by 2, but this time we're subtracting equation 3. When we do that, the x's cancel. With the y's, we've got negative y times 2 is negative 2y minus 4y gives us negative 6y. Then 2 times 5z is 10z minus negative 2z is the same as 10z plus 2z, which is 12z. And then 2 times negative 2 is negative 4, and minus 8 gives us negative 12. So now we have gotten rid of those two terms, and we just now need to get rid of that negative 6y. I'm going to rewrite the first two equations because we want to keep them just like they are. We only want to get rid of the y term in the third equation. So I'm just copying these now. And then to get rid of this negative 6y, what we can do is we can double the second equation. We can multiply it by 2. That would give us negative 6y here, and then we can subtract the third equation from that. So 2 times equation 2 minus equation 3. If we do that, the y's end up canceling because we've got negative 6y minus negative 6y. And whenever you subtract something from yourself, you get 0. Now let's look at the z's. 2 times 6z is 12z, and 12z minus 12z is no z. So on the left-hand side, everything cancels and we're left with 0. Then on the right, 2 times negative 6 is negative 12, and negative 12 minus negative 12 is 0. So in this situation, we end up with 0 equals 0, which is always true. And when we have an equation that's always true, what that means is that we're going to have infinitely many solutions, which I'm going to write now, infinitely many solutions. However, we can be more specific about what these solutions are, because it's not as though we've run out of information. We still have a system, but this time it's 2 equations with 3 variables. And the way that we do this is by solving this second equation for one variable in terms of another. We can solve here for y in terms of z, and then once we've done that, we can also solve for x in terms of z. And if we write all of our variables in terms of z, that actually gives us a way of putting parameters in for what the solutions must look like. So let's go through this process. It'll feel weird at first, but later on you will see this in Calc 3 and it will make a lot more sense. So we want to solve this second equation for y in terms of z. So we have negative 3y plus 6z equals negative 6. So we can subtract 6z from both sides to get that y term alone. So negative 3y equals negative 6z minus 6. And then to get y alone, we divide both sides by negative 3. This gives us y equals 2z plus 1. And once we know what that is, we can plug that into the first equation, and then we can solve for x in terms of z as well. So we've got x minus y minus 5z equals negative 2. We're going to plug in what we have for y. So this will be x minus the quantity 2z plus 1 minus 5z equals negative 2. When we distribute this subtraction, we get x minus 2z minus 1 minus 5z equals negative 2. We can combine the z terms. X minus 7z minus 1 equals negative 2. And then if we add 7z and 1 to both sides, plus 7z plus 1 plus 1 plus 7z, that leaves us with our x by itself on the left-hand side, and then negative 2 plus 1 is negative 1 plus 7z. Looks a little bit nicer if we write it as 7z minus 1. And so we've got x equals 7z minus 1, y equals 2z plus 1, and z just equals z. So we've got all three of these in terms of z, but we're going to do even one more thing. Instead of writing them in terms of z, we're going to replace z here with the variable t. We're going to let z be a real number t. And so when we do that, we've got x equals 7t minus 1, y equals 2t plus 1, and z equals t. This is called a parameterization, and it turns out that this is a parameterization of a line. This is a line in 3 dimensions, and it turns out that all of the solutions to our system of equations here fall on this line. You will see parameterizations in Calc 2 and Calc 3, which is a couple of semesters away, but this is something that leads into a topic that you will end up seeing there.